Welcome everyone. My name's Chris Atherton. Senior Research Engagement Manager at GÉANT. I'm the subtask leader for the Work Package 6 Task 1 Fibre Sensing subtask, which is organising this meeting today for this Infoshare on State of Polarization based sensing on optical fibres. There's still a few people coming into the room, but we've got an exciting number of speakers today from different vendors of state of polarization equipment, which I'll introduce in a moment. But I will quickly just go on to my next slide. So for those who are new to this, the way that we've been looking at fiber sensing is that there are two types of approaches to fiber sensing. There's distributed fiber optic sensing, which uses reflections from impurities in the fiber when a laser that's been injected into the cable reflects some of that laser light back. And that's used to measure strain along the cable. The other approach is forward-based transmission sensing, and this is things like state of polarization and some of the interferometry approaches that exist. And this is where, at the other end of the cable from where the laser is injected, mostly, you're able to observe changes in the position of the laser as it exits the fiber. For those who are interested, we did run an Infoshare on distributed fiber optic sensing that was mainly focused on DAS, or distributed acoustic sensing. You can find that information or that previous recording on our wiki. But today we're going to focus on state of polarization technologies. So far we've got these lovely people who have agreed to speak today: Benjamin, Steinar, Annalisa, and Jan. And then each is going to go through the different technologies that the organization's developed. And then we'll have a discussion and wrap up towards the end.
Thank you, Chris, for the introduction. And thank you for the opportunity to present the possibilities of logging the Stokes parameter with our polarimeter today. So let me just briefly give an overview of our company. We are founded in 2010 as a spin-off from University of Paderborn, and as of now we are still located in Paderborn in Germany. Our company is focused on everything related to polarization. So for example, we have a polarization controller which can stabilize the polarization. This can be used, for example, for demultiplexing of polarization multiplexed channels. We have also a polarization scrambler, which can generate fast polarization changes with a defined changing speed, yet up to 80 megaradians per second. And this device can also create such a cyclic pattern of polarization states, which might be useful, for example, for recirculating loop experiments, or also for measuring the Müller matrix of optical devices, which then contains the optical properties. And of course, we have our polarimeter. That's the part of our talk today that can measure the state of polarization and record it. In my talk, I will, since I am the first one to speak, give a brief overview about the definition of polarization, Poincare sphere and Stokes vectors, so that we know what we are measuring. Then I will show the principle of measuring and how the polarimeter is doing it. I will show the features of the polarimeter, such as the graphical user interface and some of the results and evaluation. Let me say already at the beginning that we do not focus too much on evaluation. Evaluation always depends strongly on what you are looking at or looking for in your data. So we mainly concentrate on measuring and recording the polarization. So let's begin with the definition. You probably all know the light is an electromagnetic wave, and the electrical field oscillates during transmission. Transmission direction is here, and the oscillation in this example is in vertical direction or y direction. So we call this vertical polarization. This may be mixed with another wave, here the green one, which oscillates in x direction or horizontal. And if it happened to have 90 degrees of phase shift and equal amplitudes, then the electrical field vector would make a circle in time. And if the phase shift would be of opposite sign, then it would rotate in the other direction. These two cases are called circular polarization, right circular and left circular. And these are special cases. In the general case, the two amplitudes of the waves are not equal, and also the phase shift is not necessarily 90 degrees. So the general case is a polarization ellipse like depicted here. And this ellipse has 2 degrees of freedom. It has 2 values that defines its shapes. One is the ellipticity angle epsilon. If epsilon is 0, then you're oscillating just in one straight line and you have linear polarization. And the other is theta, the azimuth angle. This defines the orientation of this ellipse with respect to the x-axis. There's another very useful representation of the state of polarization, which is the Poincaré sphere. Here you see we have the identical angles, but they are doubled. Here are 2 theta and here are 2 epsilon. And with these 2 doubled angles, they span the unity sphere in the Stokes space called the Poincaré sphere. And you see here if epsilon is 0 and we have linear polarization, then we are on the S1, S2 plane of the sphere, having horizontal or vertical or minus 45 or 45 degree polarization. And if epsilon happen to be plus or minus 45 degrees, then we are at the poles of the sphere where we have right circular or left circular polarization. So with epsilon and theta, we can set up a vector with 3 parameters in the sphere, which represent a point on the surface of the sphere with S1, S2, S3. And the fundamental polarization then would have a 1 or minus 1 in one of the axes. So we are at one of these dots for the fundamental polarizations. There's another representation or another additional factor in the Stokes vector. If we have an additional parameter S0, which is the power of the wave here, and we multiply the other parameters S1, S2, S3 also with the power, then we get the Stokes vector with 4 parameters. And also here we have added a superscript or an overbar. The overbar means averaging in time, and so it may be that during measurement the epsilon and theta changes, which means that the length of the vector of S1, S2, S3 is shorter than the value given by the power. And the quotient of this gives us the degree of polarization. So in this representation, we have 4 degrees of freedom. 1 is the power of the wave, 2 for the state of polarization, and 1 for the degree of polarization. And for this vector, we have different normalization types. In PM1000, for example, you can always normalize S1, S2, S3 to the length of 1 and so forth. So now that we know how the polarization is represented, we can think about how we can measure it. In principle, we must only measure that direction in the Poincaré sphere in which the power is transmitted. And this can be measured by just measuring at 4 different Stokes vectors. We call this the analyzer polarizations. And in principle, they could be just distributed over the sphere, but there is an ideal case where these 4 polarizations form a tetrahedron. So the red dots are on the front of the sphere and the blue is in the back. So this difference here has the same length as this. So it's really I really try to draw a tetrahedron. So then these 4 analyzer polarizations must be separated from the wave and measured with a photodiode. Then you have 4 photocurrents, and this gives you again 4 degrees of freedom as the general Stokes vector. The signals are then amplified and digitized with an ADC, and all this you have to have 4 times for each of the analyzer polarizations. The optical part, separation of analyzer polarization, and the photodiodes are integrated in our polarimeter head, and the rest is analog electronics on our PCB. And then we have the 4 digitized values of the photocurrents and can use measured calibration metrics in our FPGA to calculate the 4 Stokes parameters. And then we apply normalization and we can go forward either with storage or with further processing. All this is done in an FPGA. So this is how our hardware looks. The optical part, the polarimeter head, is here on the left side with the optical input here. Then inside the optical components for separation of the analyzer polarizations. And here at the bottom, you see cathode and anode of the 4 photodiodes. This polarimeter head is then soldered onto our PCB at this place. Then here are the analog electronics for amplification. Then here are 4 ADCs. They are on the back side of the PCB, so we can't see it now. And then the signals go into the FPGA with attached memory as a buffer, so we can process them. And on the top, we have the interfaces to communicate and transmit the data to the outside world. So most time we build this hardware into desktop instruments, like seen here with the front and back of the instrument. Also, we build it in rack mounts, or if you want to integrate it into your own hardware, then you can also get it as a module, so just the PCB. In the desktop instruments, you have a small menu with possibility to set the most important settings here in the menu. And on the back side, you can connect it to your network or your PC. We have an Ethernet port, we have USB port and SPI, and each of the port, they differ a bit by speed, but and one can say roughly a net data rate of 400 megabit per second is reached, which would be 6 megasamples per second. This depends a bit on what you're doing on the PC side with the data. If you do then some processing, that might be a bottleneck that brings down the transfer rate. We also have 2 BNC ports here, which lets us synchronize the polarimeter to other equipment, such as our scrambler or a laser, which may perform a sweep and synchronize the measurement to the optical frequency. And we can also connect 1 pulse per second real-time clock source to one of the BNC ports, so that the samples are taken with timestamps corresponding to the real time. We are sampling internally always at 100 megahertz, and you can adjust an averaging factor to bring down the sampling rate and apply averaging also to reduce noise in the measurement. We provide software such as a graphical user interface, which can be used under Windows, but we give also examples or scripts in MATLAB and Python, which we use under Windows and Linux. So this is how to get data from the polarimeter. The easiest or the simplest thing is the data stream. This means that you just configure a constant sampling rate in the polarimeter, and the polarimeter will just put out the SOP data as a stream with no more additional information. And at the PC side, then you can process the data in real time or just store it on the hard disk. Then there are some recording types which use the memory of the polarimeter as a buffer memory. The buffer is divided into memory blocks. The block size is defined by the ME, memory exponent. So with a memory exponent of 10, you would have a block size of 1024 samples. And in the easiest recording type, you just press a recording button in the GUI or start it with a script, and the polarimeter will record one block and then transfer it to your PC, and you can analyze what happened in this block. The next recording type is triggered recording, where one of such blocks is used as a ring buffer, where the polarimeter keeps cyclically recording in the same block until some event happens. And you can define what such an event is. It may be that this is the surpassing of a given SOP changing speed or a drop of power or something else. Then it is detected as an event, and it will keep on recording post-trigger events and then leave this block and go to the next block. And the left block is then transferred by the GUI or by your script to the PC and marked in the polarimeter as transferred, so the polarimeter can overwrite it if other blocks are already recorded and it needs to go on with the self-log. This is useful if you're looking for rare polarization events, such as lightning strikes. You would keep, maybe you would keep hours or days in the same block because no event happens, but then you have a lightning strike and then it will be stored in this block. And in the transfer data, you have the pre-trigger data, then the event, and then the post-trigger data, such as you expect it with an oscilloscope, where you have the trigger edge in the middle of the window. So the next recording type is dynamic undersampling, endless recording. So this goes through the blocks one by one, but it stores a sample only if it differs by the previous sample by a defined threshold. This saves a lot of memory space if polarization changes that are measured are very small. And so you can cover a lot of time with the memory and keep up with transmitting the memory to the PC, and then again mark these blocks as transferred, and the polarimeter can overwrite it. This is the main GUI window for taking the most important settings, such as optical frequency. You can apply the averaging here. So ATE stands for averaging time exponent, and the resulting sampling frequency in this case is 2 to the power of 10 times less than the 100 mega samples. So we reach 97.7 kilosamples per second. You can here then define the block size. In this case, memory exponent is 20 for one about 1 million samples per block. And then you can go on with one of the recording types to record the data in the memory and then afterward transfer it. In this case, we have dynamic undersampling and set the threshold to 0.005 radians. And then here in this window, you see how many blocks are already recorded, what's the current recording address, and you can press the Start Saving button, and then the polarimeter will download each of the already recorded blocks. On the left, you have 4 additional windows that I show you now. Maybe the most important, maybe the Poincare sphere, which shows you what happens actually right now with the polarization. And we see here there's a rotation around a great circle on the Poincare sphere. Then if we download data from the memory, we can look at it in an oscilloscope mode, and we see that the Stokes parameter here perform sine-like curves due to the rotation around the sphere. And instead of the power value given here, there seems to be a bit of PDL here. We can also display the SOP speed that has been calculated or perform an FFT of the Stokes parameter. And the other windows are histograms of the SOP speed here and of the optical power. So let's look at some results obtained with the polarimeter. This is an experiment several years ago. We dropped a hammer onto a cassette of DCM fiber where several kilometers of fiber are inside, and the mechanical shock brought the polarization, which was stable before at the front here, far around the sphere. And looking at this, we had the beginning of the event here with very fast fluctuations. Then the fluctuations became slower, and after 200 milliseconds or so, the polarization was stable again. This was recorded in the event recording type with the threshold set to 10 kiloradians per second speed. This is just a zoom of the start of the event. In the same recording type, we have also recorded emulated lightning strikes. Lightning strikes typically move the polarization from the stable start in very, very fast speed, and then go back to the same value in a bit slower speed. And we have programmed our polarization scrambler in such a way that it generates a kind of these changes. Here the blue curve is 20 megaradians per second for 240 nanoseconds, and then going back with the opposite sign with the speed of 2 megaradians per second for 2400 nanoseconds. And we recorded these events also by the event recording type. The data can be transferred and stored in files, of course. One possibility is to use text files. They have the advantage that you can just open it with an editor and look at the data. At the beginning, we have the timestamps, and then the first column is a relative timestamp in 10 nanoseconds resolution relative to the starting of the recording. And the other columns are power in milliwatt, and then the 3 Stokes parameters, 1, 2, 3. The disadvantage with the text file is that the PC needs processing power to generate these strings with characters. This can be a bottleneck when you want to download and store the data as fast as possible. And also the text files consumes some space on the disk. Here we have 1 million samples, and the file size is nearly 58 megabyte for the 1 million samples. As an alternative, we have binary files where the data is stored in the same format as it is transferred from the polarimeter with integer values. We have a header that's still in readable format, but then you have the data just that it is received. This reduces the processing power and also brings down the file size. Here we have only a bit more than 16 megabyte per file with 1 million samples. And at last, we have one continuous recording example. We took such a file and then evaluated it with Python. We took about 3 seconds from the file here. Here you see the evaluation of the Stokes parameter. You see very fast fluctuations here, and the script calculated the SOP speed from it. And very often you are at the speed of 1000 radians per second, but here the speed is dropped down a bit. If we zoom in on the data, we see that we have again such an oscillation around the sphere that we've seen before. And at this place, we have the top speed of 1000 radians per second. Usually, we look at the speed using speed histograms to see which speeds occur during the measurement. We see that most of the time, a speed of 1000 radians per second was reached, but also lower speed occurred with lower probability. You can as well do an FFT of the Stokes parameters. We see here we have a high peak at 160 hertz. And if you multiply the 160 hertz by 2 times pi, then again you are at the top measured SOP speed of 1000 radians per second. As I said at the beginning, we do only very simple analysis of the data because you probably know better what you are looking for in the data. For example, I have seen a lot in the publications, spectrograms, where you have the evolution of the spectrum over time. This is all possible. We give example for evaluation in MATLAB and Python, such as this, and then you could extend these examples. But if you are missing something on the sampling or recording side, feel free to approach us and discuss. We are eager to accommodate your needs, such as what we plan in the future, display with Poincaré sphere at the instrument or standalone unit with a large hard disk inside, so you can put it without extra computer and without any connection, and it will log the SOP for a long time. And when you have time, then you can connect to it and download the data. That's the end of my presentation. Thank you for your attendance, and I'm happy to receive questions from you.
So my name is Steinar Bjørnstad, and I'm from Tampnet. And Tampnet, we are actually a telecom operator, offshore telecommunication operator. We are operating in the North Sea and also in the Gulf of Mexico. We have subsea fiber cables feeding into mobile base stations in the North Sea and in the Gulf of Mexico. And we have actually a mobile coverage in offshore. But these fiber cables, they are also used for communication to the oil and gas platforms, and that makes it a critical infrastructure. Also, we are transporting a large part of the traffic out of Norway, or Nordic to data centers. So this is really a critical infrastructure that we need to protect. And this is actually what has motivated us looking into fiber sensing and going quite deeply into it. This is state of polarization sensing on a fiber spool. What I actually showed was that you can hear music if you try to put a loudspeaker on top of a fiber spool. And you can hear it with quite a good sound quality. But this is because a fiber spool is actually amplifying the state of polarization variations, because it's a spool, so it's curved fiber, and it's like 1 kilometer, that is more than 1,000 turns of quite bare fiber. So you are able to pick up quite high frequencies and with a quite good quality with this type of illustration, but it's not very realistic for what we observe on our subsea cables. So I will show you some more examples on that. And we have built a specific system for our purpose of protecting the cables. And this system is more like tailored for that purpose. So it's very different from the Novoptel. I think the Novoptel is an excellent system for characterizing polarization and to do accurate measurements. But this system is more tailored for being put into node rooms and for this specific purpose. This is our network, and this is what I was showing. And then I just went to the outline here. And then I go to this slide. So what we are talking about is really cybersecurity. So the point is that the weakest point in the chain is the most vulnerable. So rather than just protecting higher layers of communication, we are concerned also for the physical layer, the cables, and see that as part of the cybersecurity. So we need to detect that change detection. So we are looking at this change detection. So we are looking at changes in the optical path along the infrastructure, the physical changes, and we are getting reliable alarms from our instrument whenever there is some movements or hits on the cable caused by abnormal polarization variations. And we can also see if it's a displacement of the cable. So if a troll, for example, is hitting the cable and the cable is not in exactly the same path, this is something that we will see. So anchoring, of course, but with anchors it may be more serious and you actually get destroyed cable. Landslides, heavy earthquakes is another example. So this is an illustration. It's a video showing the device here on the floor. This is my fiber to the home cable that I have split, and half of the power goes into this box and half to the internet. And here is the cats coming and having some goodies, and they are touching the patch cable, and we see the impact up here. So this is a typical example. You can't see the cats with the SOP. If you had DOS, you would probably be able to see that the cats is approaching because you have much higher sensitivity in DOS. But in SOP, you actually see that there is a movement of the patch cable in this example. And the view you saw there is a Grafana view. So we use, say, standard normal tools that are freely available that you can display the results. And then I will talk a little bit about how to integrate it into the network. And this is a rather interesting thing. I noticed there were some questions about it. So what we have done, actually, it's up and running in our network now, different methods for integration. It's a dark fiber where we just put up SFP, sending continuous light into the dark fiber. It may or may not be EDFA along that fiber. If there is a EDFA, we do filtering, optical filtering out the wavelength channel, and then we put it into our instrument. If the distance is like 100 kilometers, you can go without EDFA. But with EDFA, we go up to 300 kilometers actually, with a single EDFA. So that works very well. Whenever you add an EDFA, you also add noise. and you also add noise in the state of polarization measurements, actually. So the best is to go without EDFA. Then you can go into a communication system. So we do that also on a route. Then we add what we call an alien wavelength. So that's added into ROADM. Again, we just use SFP with a laser sending a continuous signal. And by sending a continuous signal, not an on-off keyed signal, you get no interference problems with non-linear effects through the transmission system. So it's actually quite important not to send on-off keying. If you send 10 gig on-off, it may be interfering with your high bitrate communication channels. So we send a continuous wave and through the line system, and at the receiver side, we drop it, we filter it out, and we send it into our state of polarization instrument. This is not a polarization multiplex signal. It's just it's a polarized signal, and it goes through together with polarization multiplex signals, but the channel itself is not polarization multiplexed in this example. And actually, here is the big surprise. You can use the output of a transponder which is polarization multiplexed. So this is a polarization multiplex signal going through your system. And at the receive side, I believed for many years exactly what Novoptel said, that then if you try to put this into a polarization analyzer, it's orthogonally polarized, so we won't see anything, won't see any changes. That is actually not the case. You do see it. I don't know why. And this is an ongoing topic of research. But it actually works. It works in lab. I noticed this in a paper that was published, and I questioned it. They tried it in the lab. They measure with Novoptel. It works with Novoptel, and it works with our instrument. It works in the field, also in the field. I've done field experiments, parallel on the same cable, dark fiber, and this polarization multiplex signal, and it works, but sensitivity is lower. But it works for this purpose. If you just want to detect changes in state of polarization, and quite strong changes. So this is the instrument that we have built. It's a prototype. This is a prototype. We are now developing an instrument for production. This is what I would say a tailored instrument. So we measure changes. So typical -20 dBm input. Sampling frequency is here like 44.1 kilohertz. And the reason we can go up to 192, but it's maybe a better idea to go down on the sampling frequency, because what we observe in practical purposes on the cable, except from the lightning stroke, it's maybe up to a few hundred hertz maximum. And we measure only S0 and S1. And that is a simplified way of measuring. So we measure changes in power and changes in S1. And the thing is that if you add S2 and S3, you will get higher sensitivity, maybe. But if there is a state of polarization change in a cable, it will not be only one of the S parameters changing. You will see it also it in all S parameters, maybe except the power S0. Then we have a large local storage, and that enables us to store all the data we record, like 1 to 2 years of data. So we don't have any triggering of events or anything within the box. We rely on storing all the data because it doesn't really consume that much space. And we have some embedded software in this device doing edge processing, and that is for the streaming. Because if you want to do real-time streaming of data and representation, then you would like a compressed data stream, which more shows the changes, like the one I showed you in the cat video. And the raw data we synchronize to a server, and it's all built on a Raspberry Pi. So we have keyboard, mouse, and display, and we have Ethernet through RJ45. And we also, in our industrialized version, it will be 48 volts power supply. And the format of the data, the raw data, is .FLAC. It's a compressed audio format, and that actually enables you to use all types of audio tools for doing signal processing on the signal. So you really open a large world of tools by doing this. And then the process data we can stream to Network Operation Center for monitoring and alarming. So we have deployed this on quite a large part of our infrastructure, most of the infrastructure. And this is an example. It's a cable going from Kårstø, Stavanger to Oslo, like 700 kilometers along the Norwegian coast. And what we do here is to have a polarization instrument on every landing along the coast. So we measure section by section. And this is the benefit of having a separate instrument compared to having a polarization extraction from a transponder. Because typically you set up optical paths that may go all the way to Stavanger from Oslo. And what you see then is an integrated signal, and that actually don't give you a lot. It's mostly noise, because all events along the whole path will be visible, and that may be very hard to distinguish what is what. So monitoring section by section, more like a high density SOP monitoring, makes sense in practical cases. That's what we see. We do the local storage and processing. We do tunnel it all into a server. And in this server, we also have a database for the process data, which is also streamed from the unit. The process data are displayed in Grafana. And we also have management access through this tunnel. So we just connect the instrument to the network. It puts up a tunnel to the server, and there we go. So it's plug and play. So we may also give external users raw data access to this server storage server. So scalability is an issue for us, meaning that it's not one or two instruments. It's more like tens of instruments needed. And then this edge processing is an important thing, and the ability to do local storage, so you can actually get the data whenever you need it, just by going to the node and downloading it. But so far we have also been able to store all the data from all the nodes centrally. But that will, if you have many nodes and years are passing, it will requires many terabytes of data storage. So main challenge is scalability and the proactive, reliable alarming to an operation center if you want to do this type of surveillance of your cables. So this is a typical cable that has been hit many times by trawlers before it broke. And this is from a repair operation. This is an example where there was a fisherman calling us, telling that I think my trawl has been stuck in the cable, in your cable. And we went into our monitoring system and noticed there were no correlation between the time that he was doing his operations with the trawl and fluctuations in the state of polarization. So we told him that we don't think so, and he had help lifting his troll. And this is a trailer for a boat. It was not a cable. So it saved us quite a lot of money for doing an inspection. This is an example. Here we use a alien wavelength in a transmission system, and there is actually a troll hitting the cable. We see a very short SOP fluctuation because this troll is just passing over, hitting it. So it lasts for only a few seconds. Still, the frequency content of this is just typically below 100 Hertz. And we also observe this on a DAS because we have DAS on parts of this cable. But with the DAS, there is a kind of saturation when you hit the cable because it's a very strong signal, and that is a challenge for DAS units. So with the SOP, we are able to see if it's just passing over the cable or if you have an actual hit and how serious this hit is. And we have a lot of trawler crossing the cable, but normally it's not hitting the cable like this. And then we are displaying this in Starboard, which is a visualization tool with the map. And you see the cable here is the red cable here. And we see AIS coordinates, that is, all vessels are sending AIS information about the vessel and its position, which is picked up into this system. So you can actually see vessels crossing the cable. And they also send information if they are doing fishing or not. And if they are passing the cable and they have the troll down, in this case, we also have DAS, so we can see we can actually see if there is subsea activity. But the thing is that if there is a hit, it's hard to see with the DAS if it's actually a hit or not. But with the State of Polarization, we can see that. And we can even see if there is a displacement after the hit. This is an example. You have the hit, you have the sudden polarization change, and you have a permanent change because there is a displacement of the cable. So that is our prime application of State of Polarization. We have also been doing research. So Christina, which you may know, have been doing research, and this is from earthquake observation in Japan. And it was observed both with the Novoptel polarimeters and with the polarization beam splitter based instrument that we have. And we can see approximately the same type of pattern. It was on different fibers though, so it's not exactly the same, but it's about the same. And that was on an aerial cable. So that may also be an interesting application of polarization sensing because you get an amplification of earthquakes when you have an aerial cable because the poles starts to swing. So you may be able to see it with a higher sensitivity, and also it may enable you to see local impacts of the earthquake. So this is an example of excavator digging, where we have a frequency spectrogram. We can generate this with we have Python scripts, so we can generate spectrograms. What you see here, you see that it's basically below 100 Hertz, this digging. But here they are digging above the cable, and you see the cable is here, and they are digging here. So it's not a very strong signal actually, but you see it, and you see frequencies are very low. So actually the best way of localization, practical localization in state of polarization sensing, it's to have a high density of nodes. So this is 3 different cables out from the same node room, and when there is work in this node room, we are able to see fluctuations on all three cables, meaning that it's working this node room. Nothing happening on the cable, but it's in the node room because we see it on all three cables spanning out from the same node room. When it comes to some kind of timing-based localization and synchronization, okay, if it's a lightning stroke, you may be able to see it because you have very high frequency components. But remember, the delay in a fiber is 5 microseconds per kilometer, meaning if you have 100 kilometer of fiber, you are on 500 microseconds. The fluctuations we saw in the excavator digging was up below 100 hertz. That is 10 milliseconds. So the delay through the fiber is a small fraction of the frequency you have of the signal, meaning that you will need a very high signal-to-noise ratio for being able to detect it. You don't have a high signal-to-noise ratio if you go through this. So it's very difficult to use this timing-based approach for the normal polarization variations in the fiber. For the practical polarization variations that you observe with excavators, with trolling hitting the cable, but perhaps not if the cable is about to break. I have seen much higher frequencies then, and also if you have lightning strokes on the cable. So that's basically what I have. Real-time graphical user interface plot through Grafana. Centralized storage of raw data, I think is important if you want to process and correlate data from different locations. Main use case for us is it's a change in the optical path, any sudden change in state of polarization, and it need to have some strength, and then we have an alarm on that. And I think compatibility on the output is important, like opening up for using like more say standard tools like Grafana, audio processing tools, and so on. Okay, thank you very much.
I'm Annalisa Morea, and I work. I work in Nokia into the optical network division. So for people that doesn't know, Nokia is a network vendor provider, and we are able to cover the end-to-end network solution. So IP, wireless, but also optical networks. And into this presentation, I will give you an overview about the studies that we are doing in our business unit for obtaining some solution about the state of polarization. The core of telecommunication, allowing the transmission of high data rates, is ensured by the optical network. But one of the main difficulties in the optical network management and operation consists in its scale, that is the number of nodes, links, without thinking about the capacity of the optical channels. And then there is also the heterogeneity of the networks. Here we show that there are fibers that are underground and may be nearby rails or highways in a urban context, but also aerial fibers and also subsea. Beside the network, the physical infrastructure, we have the optical channels that transport up to terabit per second each channel. And this channel may transport several services with different level of agreement that are called SLA. We have from low priority traffic, like our personal private emails, to very sensitive traffic that may be the bank transaction and recently also the AI workloads. Once that an operator is able to correct set up the network and all the services, one of the most difficult tasks consists into the network operation. above all because the network infrastructure is threatened by different types of events that may be associated with hardware failures, but also some events that are originated by humans, but also natural environment. So anyone can imagine that the loss of data, even a few seconds of downtimes, means the loss of many data that may be associated to services and very high sensitive services. And for an operator point of view, this translates into penalties, so operational cost. And it becomes so important to prevent the downtimes and so the loss of this sensitive traffic. How we are thinking to give to the network operators some solution for preventing this downtime. So by exploiting how we can from the most deployed resources into the optical network. And these resources are the optical fibers, both in submarine and terrestrial context. Into this map, that is a public map that you can find here, we give you an idea about the capillarity of the optical fiber deployment. With the gray lines here, we have the submarine cables, and with the blue one, the terrestrial ones. By GÉANT, as it was anticipated by the introduction of this webinar, there were two sessions organized, and the first one was presented last November and focused on the distributed sensing, and now there is this one about the SOP. Among the SOP that is a part of the forwarding technologies. But during this speech, I would like to show you that SOP-based sensing not only is related to the forwarding, but also, in some cases, to the backscattering. So here I will quickly give you an idea about the main principle of the light propagation into the optical fiber. A little bit some concept that were presented during the first presentation. So the light is an electromagnetic wave that decouples into electrical and magnetic fields. Usually for our scope, we measure the electrical field. And one way for also measuring this field is by the polarization. Polarization that gives us an orientation of the electrical flux during its propagation. Usually the light into the optical fiber is randomly polarized. And here we have some example about the representation of the Stokes parameters that give us an idea about how the electrical field propagates. These are the Stokes vector. This is the Stokes vector by the 4 Stokes parameters that was also presented into the Benjamin presentation. And so these 4 parameters gives us an idea about how the electrical field is propagating. The S0 parameters gives us an idea about the overall electrical field, and then the S1 how this field, this wave is propagating along the X or Y axis. And so, for example, the horizontal transmission is given by the S1 parameters equal to 1, while the vertical transmission with this parameter equal to -1, and this can be also deduced by this formula. Then we have, as was anticipated before, the fact that there is the propagation follows not a very circular but more elliptical waves, and this behavior is described by S2 and S3. And into S3, for example, we have the idea about the circular right-hand transmission with the S3 parameters equal to 1, and the left-hand transmission with the S3 parameters equal to -1. A fiber results to be decomposed by a succession of several birefringent elements, and with their own polarization axis, as it is here represented. Then the optical fiber has also a shape that is not completely round, circular, and this has also an impact on the polarization state of the light. So in the end, the state of polarization that is received into the end point of a fiber is completely decorrelated from the polarization at just after the transmitter. Into this slide, I just present to you the monitoring of the polarization status, S1 with the blue line, S2 with the red one, and at S3. These values are normalized with respect to S0. Here, so there is the plot of these three Stokes parameters, but it is also possible to represent these Stokes parameters by this Poincaré sphere, where the three-dimensional the 3D parameters are represented, and these the coordination of these 3 points are reported here into a part of the surface of the fiber. What we can observe here, there is almost no events that are impacting the fiber, and what we observe that the 3 parameters are present quite like a noise for the 3 Stokes parameters, and are moving around a small section of this Poincaré sphere. The fiber so has this different section with its birefringent zone for each of these sections, but then we may have some stress that impact the fiber, and then may also have an impact on this state of polarization. So we may have stress that can be static, like for example the conduct, the curvature of the conducts where the fiber is put for the installation, but then we may also have some dynamic stresses, like some vibration or someone that moves the fiber. And so when we have a stress that acts on the fiber, we will see that the status of polarization will change. So starting from a given point, this polarization will change, and for example at the receiver we will observe these changes, and also measure these changes. Here into this slide we will see how an external stress has an impact on the Stokes parameters, and how then it is possible to recognize this event by observing the 3 SOP values. Into this example we will use a robot because we are not able to use a load to have cuts for emulating any type of events like what we saw into the previous presentation. And the variation of the SOP status can be reported for just S1, S2 or S3, and may be also reported into the Poincaré sphere as it is here represented. And what we can observe is that the fluctuation variation are not into a limited zone of this sphere, but can goes all around. And by the red lines are the part in front of this sphere, and the blue lines shows how these events propagates on the other side of the sphere. Now, the question is where we have to monitor the SOP. As told before, the fiber has some imperfection that is present due to its realization, above all if this fiber is done by solid like silica fibers. And which is another effect of this imperfection, is the fact that when we have a light that is propagating along the fiber, part of the signal propagates forwarding and part may be also reflected. And this means that also on the reflected part of the fiber, we have SOP variation in case. And so in the end, the SOP monitoring may be done forward, but also on backscattering waves. Into Bell Labs, we have studied different type of SOP variation detection, and into this presentation, we'll start with the forwarding techniques. The forwarding detection exploits the output of the recovery and compensation algorithm that are used into the digital signal processor, the DSP, that is inside the optical receiver. During this compensation, the compensation of the physical effects, there are also some data concerning the polarization. And so it is possible to take this information to observe, record, and observe any changes about the SOP variation. This means that the sensing is done by extracting information of the DSP that is recovering the data that are associated to real traffic transmission. So in this case, the SOP monitoring is done without requiring extra resources for the monitoring. Into the last years, we did a lot of field trial and test about the possibility of really detect any event in a terrestrial and also subsea links. And here we have reproduced some polarization variation that were recorded into these two different environments. And what we can observe is that terrestrial links are more record more events than the subsea ones, which result to be more stable. And this is also quite normal because subsea environments are quite calm in a certain way. And here into this slide, I just want to show you that there are different field trials about the proof of concept exploiting this forwarding SOP sensing, and these are some examples about a transoceanic detection about some waves and swells. And it is possible to have a connection, an optical connection monitoring over 7,000 kilometers. And here it is possible also to localize, to understand which type, or better, that some events was observed during the monitoring. Here we have another type of field trial now into terrestrial and better aerial networks. And this field trial was done in Sweden, and also in this case we could observe the variation of the SOP with reference to the wind strength, and not only how the SOP is modifying the amplitude of the changes on the three Stokes parameters, but also how these points are moving on the Poincaré sphere. And here there is another kind of experiment that we did now into a metropolitan area. And also in this case, we can observe different type of events that have been monitored. What about the backscattering monitoring? So also in this case, these are some experiment and proof of concept that were already published by our Bell Labs laboratories. And for realizing the backscattering monitoring, we now needed an extra hardware. So it is not possible to use the transponder as for the first example, but we are creating a box that gives us OFDR signals and exploits the OFDR effects, and we are propagating these probe signals along the optical subsea cable. What happens? That the architecture of the subsea amplifiers that has high loss loop back components that are these kind of couplers that allows to the backscattering lights to go into the other direct fiber contra-propagating fibers, and so the backscattering signals can propagate with on the other direction, and at the same time being amplified so that can reach the detector that is placed at the same point as the emitter of this probe. And in this way, it is possible to observe the SOP variation at a given point of my cable. And as we have these amplifiers here, it is possible to cover several thousands of kilometers. And into this proof of concept, always provided by our Bell Labs, it was demonstrated that it is possible to monitor the wall submarine cable and with the power of by measuring the power of the different spans, and in case there is some events, it is possible also to detect with a precision of 50 kilometers of resolution the events, in this case under the sea. What about the terrestrial solution? Bell Labs is also investigating some method for measuring and understanding the SOP variation when we have extra hardware into terrestrial solution. And this extra hardware, in this case, it is supposed to be placed into the ELA. So different strategies for providing the SOP monitoring that have been under studies in our laboratories. We have a lot of proof of concept, field trial, and demo. Most of them are public, have been already published in at Koch, OFC, or other journal publication, and can be found easily. And obviously, each of these methods has its own advantages and drawbacks. Into this plot, I tried to synthesize the pros and cons associated to these different technologies. And with the DSP, the main advantage is that this is a low-cost solution that is integrated into the hardware that is usually used for transporting the real traffic. So in the end, we just need an extension of a software associated to the network management tool. But on the counterpart, it is not possible to provide an accurate event localization. But I want just to do with you a small spoiler. That is that at next OFC in March, our Bell Labs laboratories will present a study where they show how precise, accurate will be the localization with this technology. On the other hand, we have the backscattering-based solution that is more expensive because we need extra hardware that has to be deployed into the network, but on the counterpart, it has a very good accuracy of the localization about the localization of the event, and at the same time, for its nature, it is possible also to understand if this event is moving or not. So in case there is a navy or a car, depends then on the environment that we are monitoring, it will be possible to understand in which direction this event is going. And then once that we have detected that it exists an event, it would be nice also to recognize that event also for understanding the type of prevention action that the customer has to do for saving its traffic. And here into this slide, we have some tests done into our laboratories where we have a robot doing some movement around on the fiber. And what we can observe that each of these movement has a different signature on the SOP variation. And so in the end, perhaps that we can say that we have a proper signature associated to each event. And at this point, there is the AI algorithm that comes and helps us. Indeed, AI-enabled machine software have a unique ability to learn patterns and then provide event classification. And this is what we are doing always with our Bell Labs laboratories, where we are trying to let the machine learn about different signature on the SOP status associated to the different events, and then recognize and labelize these events. There are lots of interest of having all this type of sensing features, and we have just collected some of these use cases coming from different discussions that we had with our customer during different meetings. And so we discovered that the feature of fiber sensing and also its labeling may help them, the operators, into the network operation by making more automatic some action like the fiber characterization by detecting which part of the fibers are aerial, submarine, then also trying to detect which are the SRLG about some fiber, and also by detecting in the network which are the low or high risk fibers, and so by detecting this zone, try to avoid high priority traffic to pass through this zone, this area. And then it is also important when there are some fiber breakage that occurs to provide the root cause of these events. And so many other types of these kinds of telecom use cases. But at the same time, there are some type of requirement about environment monitoring. And so it is possible also with this kind of fiber sensing to have information about storm or earthquake and also other observation about the environment. And this observation is above all required for submarine area where the setting of monitoring hardware or stuff is quite difficult to do. So this ends my presentation. If you have any question, please don't hesitate to ask.
Perhaps I would mention that Cesnet is not a vendor, it's just a research and educational network. So basically, I'm going to also thank to all presenters because almost everything was covered, especially from theory part. Okay, hopefully, okay. I'm going to talk about Cesnet Polbox, which is prototype developed for Submers project. Some of people in audience are actively participating in this project. So basically it's just, one input, and there is PC, and there is some output, so you can check what's going on in the fiber. Features of Polbox, it is really was manufactured for long-term continuous SOP acquisition, sampling rate up to 20 kilohertz for channels with certain resolution. Perhaps it's not so critical. You can, as was already said, tap existing signals, or of course you can use a custom laser source, CW or any CFP 1 gig, 10 gig transceiver pluggable. This prototype is capable to operate from original to L-band, but of course it's better to use C and L-band, but there is nothing critical. And optical power can be or should be for the standard units -15 to +15 dBm. And we have also special version which can work with signals up down to -35 dBm. For optical people, -35 dBm, it's pretty low or pretty faint signal. Just normal chassis. This is monitoring capabilities are compatible with Influx DB and Grafana. Also, you can just synchronize your files to remote file system or object storage, S3 compatible. If anybody knows S3, it's really not for faint-hearted. Sometimes it's really difficult, but it's not the problem of Polbox, it's just S3. How it works? Very, very simple. You have optical input. There are some optical components, then custom-made PCB with photodiode amplifiers, analog to digital conversion, and this embedded PC. Data, telemetry, and of course you can ask just to be alerted if something is going on. I'm not going to repeat anything about state of polarization, perhaps just this picture, because I am from NRN, so perhaps it's not so critical. I can show this picture of the gentleman. So because polarization sunglasses, we all of us known polarization sunglasses, so there is light which is unpolarized, and then it's just certain polarization, or in just common terms, certain rays of light may pass through. And of course, this gentleman may rotate his sunglasses so he can choose which state of polarization or rays of light may pass. Okay. Use cases, this is something really important for users, perhaps not for us as developers. Basically, you can detect vibrations and disturbances in fiber, and of course, in its neighborhood. For just one great example is seismic activity. Intrusion detection is just another point. You can just look after your critical infrastructures with alerting system. And what is perhaps more important and interesting for us is long-term acquisition, because you can do your analysis. It's not so easy to tell what's going on. You can see something, but it's really difficult to classify these events. Some really practical notes, because usually for these purposes, just fiber sensing, it's just golden equipment, it just DAS. There is one big difference between SOP and DAS, and SOP cannot easily tell where the problem is. And of course, this is pretty important for some use cases and end users. In principle, it's quite simple, because you can use this speed, distance, time equation. Distance you can calculate if you know speed and time, like vehicles. There is only one problem, because photons are pretty quick, cars or vehicles traveling this speed. So if you want to measure something really in 1 nanosecond, it's 1.2 meter, microsecond 200 meters, and in millisecond, it's 1 kilohertz sampling frequency is 200 kilometers. I hope these numbers are okay, should be. What does this mean? You need really, if you want to tell where is something going on, you need really accurate timestamping methods like Wait Rabbit. For example, PTP, well-known precision time protocol, with its precision and accuracy, it's just not good enough. What I have just some hands-on experience with coherent transponders, and sampling is every 1 millisecond, 1 kilohertz. And this is clearly not good enough if you want to localize something really precisely. So they can report SOP. Of course, I know only 1 or 2 coherent transponders, but resolution, spatial resolution is limited. Okay. Example data from Submerse project. Here you have these SOP changes and these 4 values. They are not Stokes parameters, but raw data from 4 photodiodes. And here you can see waterfall. What is really different from DAS, there is time on this axis, but there is no distance, but it's just frequency. So we can see some pattern, perhaps some higher harmonics or something. This is, for me, I cannot tell you what is it, just some changes. Data format, raw data stream, so you can really see these 4 parameters. This is for unit which is not calibrated. Of course, you could use something which is called Miller matrix, but again, it's not for faint-hearted, and you can produce Stokes parameters. This is not so critical for waterfall. The waterfall would be exactly the same, but if you want to compare different pole box units or even SOP equipment from different vendors, then it's a good idea to calibrate all units. Data format, it's really recorded as raw time series, and it is stored locally, especially for Mr. Atherton HDF5 format with some metadata. So you can store it locally, can be synchronized to the remote storage. Because everything was done by Cesnet guys of this team, it is really compact, self-descriptive, and you can read it without any problems using Python or MATLAB. What is really interesting, because there is no standard for SOP data storage, so we really work hard on this. There is some initial draft, and definitely we do hope just to publish something for, of course, for discussion. Depending on input signal, the SOP data stream is 6 to, let's say, 13 gigabytes daily. And it is big difference when you compare it with DAS data, because there is perhaps some lower limit, 1 terabyte per day. I'm pretty sure, sorry, it would be even more. An actual data file is rotated each hour. You can configure it. And what we mean rotated, just renaming. It's not deleted, because you do not want to work with a file which is 1 terabyte, but I think even 1 gigabyte, it's really difficult to work with. Again, data format and metadata, I think it's quite self-descriptive. You have creator, description, number of channels. There is typically 4 for SOP. There would be much, much more for DAS, sampling frequency, etc., time zone. So definitely this is perhaps not so critical, but important. And we also have definitions for 2 events. One is interval, of course, from T1 to T2, and event, this is single point of time. So basically, again, it's up to you just to tell what's going on. And of course, start and end, it is, I think, quite easy to understand. So you know what is in your HDF5 format or file. This is really something for me really interesting. You may compare data from SOP and DAS. They are aligned. This is from Submer's project. You have something like Polbox 137 and here 149. It's just ID, and I was told that this is the last octet of IP address. So it is really interesting because all channel summary you can see sort of, for me, this looks like chaotic. Here on this SOP, you can see something more and really nice from DAS. So you can see the time is the same. Here we can see distance, and this is frequency. On this part, on our right-hand side, again, it's for me, this looks even better for SOP, just with some more details, but DAS, it's almost empty. We can see here now something. So the real comparison of SOP and DAS data, it's something quite, I would say, unique, because again, we have no idea what's going on here with SOP. We see something, and also frequency here is really, really low, up to 20 Hertz, because with SOP, you can easily go up. And this is again from Submers. You can see it's really, I don't know if you can see it, but there is something, some sort of wave at 5.5 kilohertz. Also here is something 7.5 kilohertz. Again, I have no idea what's going on. Perhaps this is some the problem with data, but this is really, you can see this sinus, sort of sinus wave. So it is really, again, we have data, but it's very difficult to tell what's going on. This is not from Submers, this is from some terrestrial optical fiber here in Czech Republic. So again, this classification was done by a human eyes of Martin Člapák. So in this blue circle, you see something, you can see some pattern. And these 2 red circles, they are red and blue because this looks different. Again, I don't know, I hope you can see it because my monitor is quite big. So you can see there is something going on, again, in frequency, which is pretty low. It's hertz, not kilohertz. Perhaps some, some trains or something, but we are not sure, not 100% sure. Analysis tools. So I think it's really what I already said. It's just you make your own script in Python because there are some known tools. Perhaps not so, because for DAS, there is also some Python library, but for SOP, there is really nothing. Just command routines, you can use time, frequency, plotting, subroutines. So it's not so, really nothing that special. But for live demonstration, my colleagues developed this GUI, which is called PoLive, and you may record and display what's going on in time and frequency domains. And you can also manually annotate what's going on. We also work on automated event detection with several approaches. There is no time to go into details. And again, in time and frequency domains. And this is the problem, unlabeled data. We see something, but we cannot say what it is. Here you can see something where there is some vibration desk and source. It means laser, pole box, and everything is located on the same vibration desk. So you can see in time sort of vibration were set to higher frequencies. So basically you can see what's going on here. And this is just from, if you can, of course you cannot, look from the side of the monitor, you would see something like that, this relay frequency distribution. I prepared picture because it looks that there are two groups of scientific or research people. One, it's for more natural to see like oscilloscope in time domain. And of course, when you use spectral analyzer, you can see what's going on, but it's just frozen in time. So basically this is waterfall, SOP, we can see time, it's just running, and you can see frequency, and this is side view. You may imagine, if it's not clear enough, these frequency peaks or hills pointing towards you or in opposite direction. So that would be 3D picture, again, what's going on. Now back to conclusions. I think I'm pretty quick. SOP is really great alternative to DAS because there are also interferometric methods. SOP producing really much less data and can detect higher frequencies very, very easily when compared to DAS, because just to detect 10 kilohertz with DAS, you can do that perhaps, but the huge amount of data, I cannot imagine how huge these files would be. Localization of events, it's not easy, but possible. There is great reference to OFC, and again, it is really just this basic principle. Perhaps you may remember from elementary school these tasks, math task, train A, departing from location B, and in the opposite direction, train C, departing from D, and just calculate when and where they may pass. So it is possible. They did some with customized FPGA. For Cesnet pole box, it's prototype, as I said. And now it's just transfer of know-how to licensed partners. So it is our hope you can buy it. And big thanks to colleagues from Cesnet, and also thanks to you for kind attention. And here references.